talk about that. This section 3.2, the derivative is a function. Again, right? When you do things repeatedly, right? Sometimes it is better to do it just once and then come up with a formula and apply the formula for the different cases that we want, right, to solve. So let f be a function. The derivative function denoted by f prime is a new function whose domain consists of those values of x such that the following function exists. F prime of x equal the limit as h approaches 0 of f of x plus h minus f of x over h. Notice that here mathematicians are considering the base point in general as x, right? So they're going to compute here a formula that will give us the slope of the tangent line for any value of x. So that's the idea behind this, okay? So let's do that. Instead of working in particular with one value of x, let's work in general with any value of x. So for example, here it says find the derivative of the function f of x equal x squared. F of x equal x squared. And they are giving us here x as our base point, again, in general, right? In general. So what should we do? Well, let's follow the formula, right? Let's follow the formula. Here, f prime of x is equal to the limit as h approaches 0 of f of base point here x plus h, because the base point is general now, minus f of f evaluated the base point is x in general over h. Let's see what we get. Again, right? This is the base point now, x. You're gonna compute the slope of the tangent line for any value of x. So now the function is the square function. Remember, this x is just a placeholder. So this will become limit as h approaches 0 of x plus h is square, right? Square minus f of x, x squared. All that divided by h. Simplifying, meaning foiling this out, x plus h squared is just x plus h times x plus h minus x squared over h. Yeah, and I see in the chat some students. Yeah, very good, ma. Yeah, very good. Yeah, this multiplication, guys, when simplified, should give us the following, right? X times x, x squared, then x times h, but right after that, x times h again. So twice xh, right? Together, when you combine like terms at the center of this expansion, plus h squared here, minus x squared, right? Minus x squared. Professor, where are the cancellations that you promised? Well, the cancellations are here, guys. And indeed, if you don't see cancellations, check your work because probably something went wrong. These cancellations will always appear because the idea is to eliminate this h that is causing this undefined situation when you try to evaluate this expression, right? Look, this time I'm going to factor out h, but you know that h also can be divided into this, right? Doesn't matter. Factoring out h into this is just 2x, h into h squared, h over h, such that here we can cancel h, right? H cancels with h. Finally, I get this limit as h approaches 0 of 2x plus h. Now, applying a direct evaluation, h is just 0. So this ends up being equal to 2x plus 0. Finally, look, twice x. I was able to figure out the derivative of this function, the square function in its basic form, right? And I was able to generate or to get this slope formula. So from now on, if f of x equal x squared, then maybe we should write this like this. Its derivative is going to be twice x from now on, right? We don't have to repeat our work. So from now on, if f of x is equal to x squared, then its derivative will be just twice x, right? We proved this here. Very good. So now I want you to work on something here. Let me see. Can you try this now? Number 7. This is a function. They say find f prime at any value of x, the derivative, right? The derivative for this function. And I'm going to give you a hint. The derivative using limits by definition is this. The limit as h approaches 0 of f of base point x plus h minus f of x all divided by h, right? Try to do this, guys, and use this formula, right? F of x here equal x squared plus 5. Try to figure it out. I'm gonna write the expression for x of f of x plus h. That should be just x plus h squared plus 5, right, within brackets, minus f of x, which is this, within brackets. I will write this, right, f of x. And you're supposed to take the limit of this expression as h approaches 0, right? This divided by h. Simplify algebraically, and you should get your answer. I see. Ma. Excellent. Yeah, you got it. Yeah, very good. Excellent. Excellent. Yeah, you got it. Very good. Very good. Very good. Very good. Very good. Yeah, it's at this point it's tedious, but later on we will develop some formulas that will help us. But this is going to be needed on your homework, guys, for the scaffolded question. So Miguel, also very good. Very good. Yeah. Let's work this out together, right? Let's work this out together. So remember, the expansion of this x plus h squared is just this, x plus h times x plus h, right? We gotta FOIL this out. Plus 5 here, minus, imagine here you have minus 1 multiplying over, we'll make this x squared minus x squared, and we'll make this 5 a minus 5, right? So we got this. Now, this should be equal to the limit as h approaches 0 of what? X times x, x squared, x times h, xh, but there's another h times x, together 2xh, right? 2xh. And this h times h squared. Right? This is simplified what you get when you FOIL this out. Plus 5 minus x squared minus 5. Professor, you said there will be cancellations on the way. Where are they? Well, here you can see one, 5 minus 5, 0. Here you can see another one, x squared minus x squared, 0, right? These cancellations will appear, guys. So now the goal is to eliminate this h, right? So we can go ahead with the direct evaluation. This time, for the sake of variety, I'm gonna just distribute the division. I could have factored, right? You saw that it's the same. H plus H squared over H. Now, this becomes the limit as H approaches 0 of H and H, they cancel. This is twice X, H into H squared H. Now, use direct evaluation once you have canceled this H. And this is just 2X plus 0, which is just twice X, right? Aha, professor, you got the same as you got before, twice X, the derivative of this X squared plus 5. Well, guys, think about it, right? This constant 5 is not really changing the rate of change of the whole function, right? It's a constant, right? So that is why. So when you take derivatives, really the constants, you have to think of the derivative of a constant being just 0, 0. So later we will clarify that, but try to think about that. So the derivative of this is still twice X, right? What we got before, remember? Twice X for the derivative of X squared. Very good. Now let's try, let's talk about, I think the next part. I see a question here. Get the bit confusing. Yeah. There's a lot of algebraic work. Yeah, I agree. Mm-hmm.
Yeah, and it gets tricky when you realize for X, I have to plug in X again, and then you have to look, make sure you're not doing it wrong.
Yeah, you have to do it slowly, so that we can avoid the mistake. Very good, guys. And then there's a nice comment here by Marcus. Says, does this mean that the horizontal shift also is not really changing the derivative? Yeah, that's absolutely right. Yeah, when you think of the graph of this guy compared with the graph of f of x equal x squared, it's just a shift, right? A shift, yeah. Maybe this is worth it to explore. Look, this is the graph of y equal x squared, right? The graph of this guy plus 5, 1, 2, 3, 4, 5, it's just the same parabola, but up here. But what Marcos is pointing out is that the derivative, the steepness at any point, let's say you take this point, right, is the same because these two graphs are kind of parallel to each other, right? It's a shift, it's a vertical shift. So this addition of constants will not change the derivative. Yeah, this is a good thing that you should keep in mind. Now, here, however, notice this is not a constant, it's 4x. 4x, right? So here, the derivative is going to change. I will show you. All right, let me go over this so then we can move to the last part where we have to talk about the derivative and its relationship with continuity, okay? So let me do this one. They want here to figure out what is the derivative of this function evaluated at 3. So I'm going to use this second approach, okay? I am going to find the derivative of this function in general, okay? In general. And then I will evaluate that formula that we'll get here at x equal 3. This is prime. If you don't see it, this is derivative, g prime at 3. All right, so let's do that. So I have to start by saying, okay, g prime of x in general for any value of x will be this limit as h approaches 0 of this function f of x plus h minus f of x over h. This is called the difference quotient. Now, if you do this carefully, it's going to be a lot of algebraic work. I will show you. X plus h plug into this function will give you this, right? And I rather have this inside brackets so I don't get confused. Look, this is one computation, right? It's f of x plus h. The function, to be formal, we should write here g because it's not f function, it's a g function. All right, g of x plus h is just this, right? Minus g of x. But g of x is the function itself, right? It's 3x squared minus 4x. all this divided by h, okay? Now, you know, as Ma mentioned, this is a lot of algebraic work that must be done carefully, right? Carefully. Look, there's a 3 outside. So I'm going to expand this guy as this 3 times x plus h times x plus h minus 4 times x minus 4x minus 4 times h minus 4h minus distributed here minus 3x squared minus times minus 4x. You can think of minus 1 times minus 4x plus 4x, right? Yeah, good here. And all that divided by h. Now this becomes the following. Limit as h approaches 0. Remember, there's a 3 outside. X times x, x squared. I'm going to write the answer of this expansion within brackets so we don't get confused. X times h, xh. But there is another xh here, hx together. This is going to give me twice xh, right? Twice x. This is right here once and for all, so we don't have to rewrite the whole thing. Plus h times h squared. But remember, still you have to multiply by 3, right? 3 is outside. Professor, you said simplification will come along. Here, 4x minus 4x, 0, right? 0. But here, this guy stays. Minus 4h minus 3x squared. All over h, right? Very good. So now distribute the multiplication by 3. Limit as h approaches 0 of 3 times x squared plus 3 times 2xh, 6xh, 3 times h squared plus 3h squared minus 4h minus 3x squared. Another simplification, look. 3x squared minus 3x squared, 0, right? 0. What are we left with? We are left with this limit as h approaches 0 of 6xh plus 3h squared minus 4h. But if you divide each of these components by h, you're going to get h into 6xh plus h into 3h squared minus h into 4h, right? So this will be equal to the limit as h approaches 0 or what? This cancels, 6x stays, h into h squared is just h, and this is minus 4, right? H into h, they cancel. At this point, what is left is to substitute this guy for h, right? 0, 3 times 0 is 0, this disappears, and this should be 6x, sorry, minus 4. This is the slope of the tangent line at any value of x, the derivative, right? The derivative, also known as the derivative. All right, but now they want that derivative evaluated at 3. Yeah, right? Yeah, so evaluated at 3, this derivative at the function is g, so let's be formal. G evaluated at 3, right? G is the function. G prime of 3, the derivative evaluated of 3 will be 6 times 3 minus 4. But 6 times 3 is 18. 18 minus 4 is just 14, right? 14. So this is the derivative of the function evaluated at 3. 14. So look for that here, 14, together with the derivative g prime of x, 6x minus 4, right? 6x minus 4 here, and this is the evaluation in the derivative for x equal 3. So talking about this guy. Very good, guys. All right, now there are some other exercises there that you can do at home, but I want you to try now this. Can you do this exercise quickly, and then we will talk about the relationship between differentiation and continuity. Can you do this? They say this is the graph of some function, not hard to see that this is the graph of y equal x squared, right? Or equivalently, f of x equal x squared. I'm gonna give you this hint. They say the graph of a function is given, choose the answer that represents the graph of its derivative, And remember, we already found the derivative of this function, right? So get the derivative and graph it. Which one would be the derivative when graphed? Okay. The graph f prime of x. So which of these four graphs is the derivative of this function? Or the graph of the derivative right there. And remember, I will give you this as a hint. Recall the derivative of x squared. Very good. It's twice x, right? Yeah, recall. Excellent, very good. Recall the derivative of this, we already established that this is twice x, right? Twice x, the first formula for the derivatives. F prime of x twice x. So which is the graph of twice x? This, or this? I see. The students figure this out. Yeah, Ma, very good. Marcus, also very good. Excellent, guys. Excellent. The graph of this function, right? F prime of x equal twice x. Twice x is slope 2. Rise over run 2 to 1. So choose the one I say that, right? Slope 2. And I think it's this, right? Yeah, there we go. It's 5. The run 5, the rise 10, I think. Yeah, this is it. Yeah, more experience posting. Let me just right here, 10. 10 over 2, right? 2. Very good. This is excellent, guys. Very good, Miguel. Yeah, very good. Okay, now let's talk about the relationship between continuity, which means the graph is all in one piece, and differentiability, which means that we should be able to take derivatives. This is a definition. Differentiate, this fancy word differentiate, it just means take the derivative of. When they say differentiate x squared or y equal x squared, means take the derivative of y equal x squared, right? Differentiate means just take the derivative of. Example, differentiate f of x equal x squared means take the derivative of f of x equal x squared. And we know that that derivative is twice x, right? Twice x. Now, when you successfully find the derivative of a function, meaning if you substitute x by some real number and you get a meaningful output value here, then you can say that your function is differentiable at that input value, let's say x equal a. And also we can say that f prime of a exists, means it's giving me a meaningful derivative, right? Yeah. So we will say now that f of x is differentiable if its derivative exists at all points of its domain. If you can take the derivative of any point along the domain of a function, then it means that your function is differentiable, right? Because it allows you to take the derivative at any input value. For example, the quadratic function in its basic form, f of x equal x squared, is differentiable. Why you say that, Professor, that is differentiable? Well, because the formula for its derivative is twice x, and this formula twice x can be evaluated for any x as a real number, right? The domain of this function f prime of x equal twice x is all real numbers. So therefore, the function is differentiable, meaning I can take derivative for any value of x, right? Yeah, that is why this is differentiable. Now, this is algebraically speaking, right? But how can I visually quickly know that the function is differentiable by looking at this graph? Mathematicians figure it out. Here is a fact. Differentiable functions are continuous, all in one piece, connected, right? But besides being continuous, connected, are smooth, continuous and smooth, meaning they don't show corners, they don't show cusps, they do not show vertical tangent line, okay? So no corners, no things that look like this, right? No corners. No cusps, no things that look like this. It's a cusp. Maybe like. No vertical tangent lines. I will explain to you what this is later, okay? With an example. But no cusps, no corners, no sudden turns, you can say, right? No sudden turns. Example. Is the given graph the graph of a differentiable function? Remember, differentiable functions are smooth, right? Smooth. When you think of something or a graph being smooth, try to think of the shape of a highway. No sudden turns, okay? It's smooth. So I'm gonna give you some examples here. So the first one is this. Suppose they give you this function, f of x equal x cubed. We know that the graph of the cubic function in its basic form shows this chair-like shape, right? And as you can see, this chair-like shape is not showing me any corners, any sudden turns, any cusps. It's smooth, right? So this one, yes, it is smooth. Very good. So cubic functions is smooth. What about this other function, g of x equal absolute value of x, absolute value of x? Remember, the graph of the absolute value function looks like V as in victory, right? And is continuous, right? All in one piece. But here there is a problem. Look at this guy. This is what mathematicians call a corner. Because of this corner here, then you can say that this one is not a differentiable function. The derivative is not going to exist here, because for derivative we need smoothness, right? We need the graph to be smooth. No, because of this corner, right? Because of corner at x equals 0, right? Right there. Because of that corner, not differentiable. What about this other function? It's called h of x equal cube root of x. Cube root of x, when you graph it, it shows you this. Professor, how do you know that's the graph of cube root of x? Well, guys, if you use your Desmos graphing calculator, check it out there, right? This is for a square root. We need cube root. So what you have to, you can do is go to function. No, perhaps we can just write this, right? X raised to 1/3. That's cube root, right? X raised to 1/3. And you can see there that this is what we got, right? Yeah, this is what I got here. Look, goes like this, looks like a snake, right? Increasing is this. But what is important about this graph is that when you look at the tangent line at x equals 0, look what happens with the tangent line at x equals 0. It's a vertical line, right? It is a vertical line. And remember, a slope of vertical lines do not exist, right? So this one, a big no, because it's showing this vertical tangent line, right? No, because at x equals 0, vertical tangent line, right? So this is this. The graph should not show vertical tangent lines, right? Yeah, and sometimes vertical tangent lines, no, it's low, Professor. Yeah, I don't know, guys, but I think when you were taking basic courses, right? They explain to you that there's this mountain mnemonic device, right? If you're going up, a slope positive. If you reach the top of the mountain, you're resting a slope 0, right? For a horizontal line. If you go down, a slope negative, right? What happens if you try to go against the mountain, again, this direction? You can't, right? Because the mountain is there. So here is slope undefined. DNE, right? Does not exist. So that's the idea of this. Vertical tangent lines do not have derivative. Man is suggesting infinity. Yeah, you could think of the slope of this vertical line being infinity, but also could be negative infinity. So it's not a real number. So mathematicians just say undefined, does not exist, right? When you encounter this, you have to say that this function is not differentiable, even though it looks smooth, right? But because of this vertical tangent line, not differentiable. The last example is that y equal x raised to 2/3. When you graph this function, guys, you're going to get something like this. Believe it or not, something like this. So what? Well, guys, if something is surprising or shocking to you, use your tools, right? Is this the graph of that? Let's check it out. Raised to, they want to write it within parentheses, 2/3 as exponents. It's exponent, right? There you go, right? You see? This is the graph. What is important here is that it's showing here, it's not called a corner, it's called a cusp, okay? So when you encounter these cusps, it means that it's not smooth. Nobody's going to construct a highway that looks like this, right? Because something bad will happen to the cars traveling at a high speed here, right? Here, not good, right? So this guy, because of the cusp, right, at x equals 0, no. So no here, because of the cusp. No, because cusp at x equals 0. This is what mathematicians call a cusp. You're very close to a corner, right? All right, so conclusion, guys, avoid corners, avoid vertical tangent lines, avoid cusps, okay? For you to have differentiable functions, okay? Functions. Now here comes this big theorem that mathematicians figure out, which states that differentiability implies continuity. Somehow, differentiable functions should be considered stronger compared to continuous functions, right? Because a continuous function just tells you that your function when graph is going to be all in one piece, no jumps, no holes. But differentiable functions are stronger in the sense that they are continuous, they are all in one piece, no jumps, no holes, but in addition to that, they are smooth. They are smooth, right? Smooth is important. So if you figure out that your function is differentiable at some input value x equals c, then for free, you must conclude that this is continuous at x equals c, right? And the other way around, if your function is not continuous, there is no way for it to be differentiable, right? Because differentiability, again, is stronger than continuity. Some mathematicians call differentiable functions like super continuous functions, right? In the sense that they are all in one piece, but also they are smooth, right? Smooth. All right, so now I want to go to the worksheet and there are a couple of problems related to this part, and also try to remember this for your homework, guys. They're going to give you a bunch of graphs. They're going to say why the graph is differentiable or not, explain. So try to figure that out. There is just one left, I think. Yeah, this one. Yeah, we did this before, right? In the other. So try this. Yeah, can you try this? The figure shows the graph of a function. At the given value of x, does the function appear to be differentiable, continuous, right? But not differentiable, or neither continuous nor differentiable? Yeah, let's see. Ma, yes, you made my day. Yeah, excellent, very good, very good. Good answer. Yeah, very good, guys. Yeah, we're gonna write the three conditions here. First, continuous. Yeah, Miguel, welcome back. Continuous. Yeah. Question for you guys. Is this function continuous? First, yes, continuous. Yes or no? Yes, right? Marcos, very good. Yes. Great, right? It's all in one piece, right? So this one, yes. Differentiable. Differentiable. Is this function differentiable? Yes or no? No, no. And whoever said no, why is not differentiable? Marcus, very good. Yeah. No, I agree, right? But why? Why is not differentiable? Because of the corner at x equal -1. Marcus, very good, right? Yeah. At x equal -1 here, there is a corner, right? Corner. And remember, corners are not friends of a differentiable function, right? Yeah, because there is a corner at x equal -1. Very good. Yeah, so therefore, when you choose between these three, differentiable, continuous, but not differentiable, neither continuous nor differentiable, I think it's this, right? Continuous, but not differentiable as stated. Very good, guys. Excellent, excellent. Yeah, as you can see, there is this relationship between continuity and differentiability, but differentiability always is stronger, always is stronger. I'm gonna give you a fact for you to remember. Fact, polynomial functions are continuous and differentiable. Okay, so this is one of the reasons why mathematicians consider polynomial functions to be one of the nicest, because you can always take derivatives, right? So turns out in real life, any function, no matter how crazy it is, as long as it is continuous, can be approximated by a polynomial function, and you can do work with those polynomial functions. Okay.